Hi, everybody. My name is Zach Cardwell. I'm a data scientist with Data 317. We're a data science consulting company. So just a little bit about me before we get started talking about data science and IoT. I'm the principal data scientist at Data 317. That's really just code for I'm the owner and operator of Data 317, and I do all the work too. I'm a graduate from Purdue Physics, especially when I'm talking about like sensors and all that good stuff. When I talk about how that stuff works, sampling rates and all that, that's really what I'm referencing. When part of the Purdue Physics program is that you actually have to build these sensors and understand gains and all that, and that informs a lot of the observations that you're going to see in a little bit. I've been a data scientist for about 10 years. I've worked in lots of industries: healthcare, tax fraud, marketing, retail, all that good stuff. Made a bunch of algorithms to predict things like disease. Made a bunch of algorithms that help understand, do NLP and figure out what you should write about, and found like about $22 million of fraud for the state of Indiana and raised about $40 million for the technologies that I built overall. So I'll be honest, like IoT as a term, have I worked in it? Not exactly as an IoT data scientist, but I have worked at the periphery of it. One of the things that, an introduction to a few observations on IoT, but just to kind of skip to the point. One of the things that I noticed is that IoT really has existed for decades. We didn't call it IoT, but the idea of having sensors connecting to the internet or connecting to a central server, recording observations and everything that they do currently has kind of existed in the industry for a while. I was at Marsh Supermarkets for about 10 years, and we had IoT devices in there back in 2006. I mean, we, just like this place does, we have sensors on the refrigerators that tell us if things are running out of spec. We have sensors that are detecting whether or not if there's smoke problems anywhere in the store. We have sensors that would automatically turn off the lights and control all that and do all the ordering that would kind of fall with it. IoT has really been around for a very, very long time. It's just what's happened is that it's become more of a commodity, that consumers can now purchase devices for their homes and kind of make ad hoc networks out of it and kind of apply it across the board. And that opens up a lot of promise for things that you can do with data science, the kind of data that you're collecting and everything that goes along with that. But there's significant caveats to doing any sort of analysis using ad hoc sensor networks. And that's really what I want to highlight more than anything inside this talk, because too often what I see, especially with junior data scientists, when they go in and they try and solve a problem, is that they don't spend the 80% of your time that's necessary to clean your data and to actually understand your data before just applying some model from scikit-learn or Keras or what have you, whatever the algorithm of the day is. That leads to significant issues in the downstream. You see frequently inside of the tech community here in town that people just let go of their data science teams because they don't get anything out of it. And a lot of times it's because this stuff isn't yielding fruit or yielding fruit in a scalable way. And it gets magnified by IoT devices and IoT as a sensor device to collect data. So here are some of the biggest problems that I see with IoT and something to be aware of. This isn't to say that you can't use data science for it, but whenever you're doing any of the necessary preparatory work, you should be really, really aware of. One is sampling. All sensors sample, essentially. They don't take continuous measurements of what's going on. They grab snapshots at different points of time. Now, depending on how you sample, you can guarantee according to information theory, that you have a perfect signal. But in general, the sensors kind of make that decision for you. And that right there, that yellow pattern that exists up there, you see this curve, and the green lines that come up, I know it's a little difficult from the audience to see, those represent the samples that you're taking across that. Now, you could imagine if that was poorly sampled, if you were to stretch out those lines or add more bumps up and down along that curve, you would miss a lot of the salient details about the signal that you're trying to measure. And when you see subsampling, and this is how it really plays into data science and AI, right here we have two identical images. One, though, was sampled incorrectly, and so what you end up with, you end up with this wave pattern that kind of sits across the image. If you're training an algorithm against that, it's just, the algorithm itself will misattribute that to something that's important for your data. Like if you're trying to classify that's a wall, a brick wall, or a building, or something like that. This wave pattern it will pick up on, and so if you take that algorithm and then move it over to another set of sensors, it will be based off of the wrong information that it's getting from those sensors when it moves forward. This is a huge problem, because that wave pattern isn't actually significant to probably the task that you're trying to solve, right? It is just a fact of the sensor that you're using. And so that's one huge problem. Sampling is huge. Another, before I move on, another thing that you have to be aware of, some sensors take samples at different points of time. So some will do 30 times a second or 100 times a second. And you can imagine, like, when you look at the spreadsheet that represents that, how you have to collapse that data down. What does that mean? Are you missing anything that happens in between the periods where one sensor is not recording or another sensor is recording over and over again? And those are significant issues that could really muddy any kind of artificial intelligence algorithm that you would apply, or any analysis in general. Another thing that I often see as being a problem is the validity regime. So sensors only work on a certain range. That's by nature. This blue and green plot up here is a band gap of a semiconductor. So if you have a transistor and everything, and that's how it's operating in sensors, it's operating over this. And you can gradate that in a certain way. You can pull certain tricks in order to try and guarantee a certain range of validity, but everything has a cap on what it can measure. A good example of this is your speedometer. This car can apparently go up to 170 miles an hour. Now, if you were to push the car beyond that, you would only get the measure of 170 miles an hour. So now think if you have any analysis that is dependent on those readings, right? Suddenly you're going to see that the car is going as fast, and stops. It stays at the same velocity, and so you lose any information about the acceleration. Again, this is kind of common sense stuff, right? But you'd be surprised when you just get presented with the data itself. If you don't know to ask those questions, or if you don't know to look for those problems, people will just apply models and say, oh, this is going to find a significant finding for me. And you have this problem existing inside of your data. Another problem, and this is a big one too, is quality in units. So some sensors might measure in inches, some sensors might measure in miles. Almost all of data science comes down to doing some kind of distance metric. The idea that you have this cluster of points that's described this way and another cluster over here, and you describe its similarity by its distance. A lot of times you see this in error functions and everything that, or cross entropy, what have you, but those are all essentially distance metrics of one form or another. If you don't properly correct your units, or if you make the algorithm do it for you, there is a very strong possibility that it will do that incorrectly. And so imagine if you have two measures for distance. On one side, it's 64 inches, and the other side is a mile. What is going to be valued in that distance measurement that you initially calculate if you do Pythagorean theorem? It's going to be the inches. And that actually isn't the most significant thing that you should probably be paying attention to, depending on what your use case is. Again, the red numbers and the black numbers right there, that's all about sig figs, if you remember those from high school. Those are absolutely essential to this too, because every measurement that you have has a built-in uncertainty to it. And if you're not taking that into account and you're adding, like, oh gosh, what would I call it? False precision. You can run into serious issues with any measurements or any calculations you do outside of the box as well. And we actually see this have real-world consequences. That picture of that satellite right there was actually killed by units. What had happened, that's the Mars Climate Orbiter, and NASA sent it out there, and while they were programming up the system, they swapped imperial units versus the metric system, and it ended up crashing into the planet. This actually happens across industry. I've seen this in several of the places that I worked where, sometimes it's in degrees Celsius if you're looking at refrigeration, sometimes it's in Fahrenheit, and you set your thresholds all wrong, or you have an algorithm who's figuring out those thresholds for you and you don't even know what the threshold is, and it can be set wrong entirely. And these are huge problems. I mean, if we go back, sampling, you don't know when you're getting the data, how much of it you're actually collecting. The validity range, you don't know what the upper bounds or the lower bounds necessarily are of the sensors that you're using. Perhaps you are, but if you're working with an ad hoc network or if you're just trying to do something quick, you run into issues with that and the quality of units. This can seriously compromise any sort of AI or data science that you might do. These networks have a tendency, these techniques have a tendency to magnify systemic error and or bias or how you collect the data and everything like that. And it could seriously compromise what your throughput is. So, how do we bring analytics to this stuff? Because we're not collecting this data for nothing, right? I mean, some of us want to live a quantified life, but we want to be able to make decisions about, what we are collecting about ourselves and how the sensors actually work. So one thing, a critical mistake that I see in several companies is that they don't invest in data architecture. Data architecture is essential for success in any analytics. What do I mean by data architecture? I mean someone who is actually going to look at the data coming in and organize it in a way so that it can actually be used for the purpose that you intended. A lot of times people misconstrue this as using the Ruby on Rails framework that automatically gets generated or a Django framework that automatically gets generated. In general, you can't use the data structures that are constructed that way for this kind of analysis. And so you need a data architect, especially in the case of IoT, to come in, understand what is the sampling rate, what is going on with this data, what is the quality that we have to be concerned of, what are the exclusionary factors, and what are the factors that need converted in order to actually move ahead. These transformations aren't trivial. I mean, data architects, good ones, they're artists, to say the least. I've met a few in my time as a data scientist, and what they're able to do is absolutely incredible. If they design it correctly, it will be built with scale, so you don't have to worry about doing all these on-the-fly calculations. And the biggest thing that a data architect can provide for you is avoiding variable conflation. The distance thing that I was talking about, it's very obvious, it's very possible, I should say, that those two measurements would just be distance in X and distance in Y, but you get no information about the units at all. And that conflation of those terms can actually lead to a lot of problems for any analysis that you do. A data architect's job will actually be to look at that and actually understand that and see if that's a consistent systemic error inside of your data so that you can remove that from any analysis. The next thing is that you need to pull out the old algorithm book. I've given a talk at the web conference a few months ago, and it was about math hacking. And math hacking really is this right here. You look up the stuff that the geniuses back at Bell Labs came up with, and you apply that because they were working with machines that were so slow. They had to be very clever with how they process data and how they designed the programs. It's really incredible. And some of my favorite techniques are these that are listed. So if you're trying to do any similarity detection at scale, something that you're probably going to do if you're using IoT data, maybe you want to know if the health measurements that a watch is taking seems to indicate someone is likely for a heart attack. How are you going to do that? You're going to look at people who had a heart attack and look at their measurements and then do a similarity estimate on if that person looks like someone who might have a heart attack. And these techniques right here, SimHash and MinHash, are actually techniques for that. What I just described would likely use SimHash. That's where you're estimating cosine distance. You reduce everything that you could do down to a single code, and then you look at the Hamming distance in between there. MinHash is a lot of fun. I used MinHash in the past to actually do document comparisons at scale using a keywording algorithm and then just feeding it in there. What's nice about both those techniques is that you essentially turn all these complicated calculations for similarity into key value stores are a Python dictionary, and it makes it super fast. It's constant time, actually. Well, there's some peculiarities around some of the Python hashing, but it's essentially constant time with how it looks up. And then another thing that I love is Bloom filters, which which completely eliminates false negatives. If one of the great things about this technique right there is if you can kind of look at some of the SQL queries that you have to run in order to pull reports from any data store, including IoT, but other applications itself, as almost like a hash function. The SQL is essentially going to come out to either true or false, and that's how you're selecting your rows, right? Well, you can actually encode that as a hash function to generate these Bloom filters and then separate out your data according to that, and then organize it a little bit more efficiently so that you can pull out analytics appropriately. And the specific implementations, I have the code up for minhash up there. I didn't include the hashing function. Usually I use murmur hash for that, but it's just a rehashing technique on top of it, and you just invert the index on it, and you're ready to rock and roll. Simhash is a little bit different. That came up by Google, where you apply a random number, and it represents a random vector, and it approximates the cosine distance. The details, you can find implementations of this in scikit-learn and all that. I like to code it from scratch. It's a lot more fun that way. But these are like key techniques that have really, really helped me find that $22 million of fraud and, connect millions and millions of documents together according to their topics. And they're so light, they're so cheap to perform that you can do these at scale, which is something that you're going to have to do with any IoT application. And then finally, you can use the fancy stuff. But in general, if you are going to apply the fancy stuff that you would find in a framework like Keras or what have you, you want to find reasons to not use complicated algorithms. This kind of gets to the Zen of Python thing. It's okay if they're complex, like if you're using difficult mathematics and everything that comes out of it, but you don't want it to be complicated. And the reason why is you never quite know what these things are doing. Yeah, we can talk about the math, we can talk about back propagation, we can talk about how the derivatives come out, we can go through all the calculations, but how those weights actually end up and how the connections actually come up, no one knows how they're actually working and what is actually being valued. Machine learning algorithms, as I stated before, are often biased by systemic error. If you have a system, in my case where I saw this was with recidivism, which is when criminals come back to prison. We were trying to figure out the reasons for that. There's a lot of systemic error for why prisoners come back to prison. And so it biased all the algorithms to select the wrong people as needing more services, right? The same thing happens in IoT. If you have systemic errors in how you're collecting the data that you have that come from sampling, come from that validity regime, that come from the units and everything, it will fundamentally corrupt the kind of analysis that you can provide. And this is where the horror stories that you hear about racist algorithms, about sexist algorithms, and all that that's been populating the news recently comes from, is that you have systemic error in how you collect it. There's actually a recent podcast that was pretty good from Reset, that if you're interested in hearing more stories, they're specifically talking about how you grade essays. They give a good example about it. Constrained data sources for any models that you implement. There's this big tendency to data blend. That's generally not a good idea, just for all the reasons that we've already talked about, unless you can really come up with a theory about how these things translate together. A lot of times people are recording apples and oranges rather than just fruit. And it can lead to significant issues in any data that you provide. See this a lot in healthcare. And then remember hardware constraints. This is a tricky one. A lot of these weights, when you are applying a neural network and everything, they are actually look at the weighting values. They're these huge floating point numbers, and then you start having issues with the significance that happens. And if you go from one system to another, you can end up with truncation. You can end up with a bunch of other stuff, and just the wobbling around of those least significant bits can have dramatic downstream effects for anything that your algorithm's going to produce. And you're almost guaranteed this by how backpropagation works. So that's another thing to be really, really careful about. And yeah, that is essentially the talk. Hopefully it's not too negative. I swear that data science does have a place with IoT and all that, but we do have to be careful about how we apply these models, and we have to actually know how this stuff works. And that's really the biggest thing. You can't just apply a framework and say, oh, the neural network says this, and expect to get a good result out of it or a scalable result. And if there's one message that I want all of you to take from it, it's that. So. Yeah, so any questions at all? Or?
Yeah, we got any questions for Zach?
I'm not popular. What can I say? Yeah. No, I'll take the not popular side.
So in measuring off of these various like IoT sensors, you were talking to me earlier about this, that there can be, you almost have to correct for the sensor's erraticness,
yeah,
right?
Yeah, it's not a trivial thing to do because we assume that the sensor's erraticness is normal, it's balanced in a sense, and that's not necessarily always the case, especially with how some of these electronic sensors work. It's a very tricky thing. And there's no solid answer to do it. You can't.
That was my next question. Is there a specific algorithm we just apply to specific kinds of hardware?
Oh gosh, I wouldn't have a job if that was the case. I mean, it's unfortunately, you have to fundamentally understand what's going on with the data and understand, if you do the error propagation, that's a whole discipline in the hard sciences. Is how does error propagate so that given that I measure the mass of the electron to be this. How does the error in my measurement propagate and lead to those plus or minus calculations that we have down the line? It's a tricky business. It involves a lot of math and a lot of calculus. And it's related to back propagation, really, but just in a different context.
Cool. Any other questions for Zach?
So you alluded to, various different algorithms, a little bit of neural nets with the backpropagation, but would you characterize the use of just simple time series analysis more relevant or less relevant, or it all depends on what you're trying to
exactly
predict, but could you just speak to that a little bit?
Yeah, sure.
The pros and cons of some of those.
My general opinion is the simpler the model, the better. And so if you can come up with something that is like a weighted average calculation that gets you 95% of the way there, 80% of the way there, I think that is far better than just pressing go on a model and saying, okay, there it is, there's the answer. The big thing is explainability. Because when you do crop into these errors, when you're dealing with things where the sensors might be off or you're out of the proper regime or what have you, the more explainable the model is, you can understand the consequences right away. And that's something that you can't do with a black box neural network. So getting away from the complicatedness is like the key for success in general with data science.
I guess related to that is, by using time series type analysis, you can kind of bake in the historicity of things, which you wouldn't necessarily with a neural net. Have you seen that in practice, or?
Say that again. I missed.
So if you would bake in some of that historic and the memory of the system by using time series analysis. Have you seen that in practice, or?
So again, this gets to the basics of any model that you're going to use. You're talking about the sensors and everything and how it falls out, and you're baking in the certain analysis. The problem is if you have a faulty understanding about how this stuff works, even if you are baking in the biases that occur because of those sensors in the historic case, you're not necessarily making the right conclusion about your data. It is very easy to say, well, yeah, the model, whatever it is, if you're using a standard time series approach like ARIMA or what have you, to say, hey, yeah, this will figure it out, but you won't know the cases in which it actually fails. again, this really comes down, this isn't a model question. I mean, neural networks can figure this out too if you have the proper data, but it comes down to that architecture. It comes down to understanding your data and actually knowing what this stuff means. And so often that is not the case when you watch how some of these things get applied, especially if you look into the popular media about AI and data science and all that.
You have a question?
Yeah, I've got a question. And so what is the significance, if any, of the proliferation of 5G in relation to data science? Whether it's just in terms of a wider data set,
Yeah,
a deeper data set, or
so it's
is it going to matter or is it not going to matter?
Well, so in terms of collecting data, it's going to matter. I mean, it wasn't too long ago I was talking to Bill Swords. He runs Indiana's AT&T. I think that's his technical title. I'm not too sure. And he's describing about the possibilities with 5G, and it's going to dramatically make it easier to connect. You're still going to run into these same problems just because of how the sensors work and everything that goes with that.